Hey gang, I'm sorry we have to be virtual this week, but when your bestie needs you, your bestie needs you. This is definitely a class that I really like to do in person, this particular lesson, because it's very interactive. But we're going to swap things out a bit. We're going to ditch what we were going to do for Lab 11, and we're going to replace it with the activity that I do in class. And then you guys can kind of do it at home on your own. And then when you get back to class, we're going to practice it together, kind of over the next couple of classes when we have time, because I think it's really fun, hands-on, and it helps you understand chemical equations. So let's talk about chemical reactions. And let's talk about chemical equations. Don't get anxious when you see the word equations if you're not a mathy person. These really have some pretty minimal math in them. They're more like logic problems, actually. They're a lot of fun. All right, so a chemical equation shows a chemical reaction using symbols instead of words. All right, we know that when we put our chemical symbols from the periodic table together to form formula units or molecules, we could just use words for those molecules, like we could call H2O water. But when we take those words away and we just use the symbols, we can show what's happening in different reactions. Okay, so what does a chemical equation contain? It has a reactant plus a reactant. Sometimes it has more than two. And then remember I said that arrow means yields, a product plus a product. Or sometimes it's just reactant plus reactant equals product. Or as we'll see in the presence of certain other forces in a couple of weeks when we do in lab, you can have a reactant exposed to a certain situation and it breaks down into two products. So let's talk about subscripts and coefficients. All right. The little numbers that are down below that indicate the number of atoms of an element present in a molecule or a formula unit, we talked before, these are called subscripts, okay? And this is like when you're working in Teacher Ease, you have to remember to use a lowercase letter V before a subscript. So I know that's what you are intending for it to represent. When you have coefficients, they show the relative amount of a substance. So for example, the coefficient over here would be like this 3 or this 2, whereas your subscripts over here are 2. So you have CS2, that's 1C, 2 S's. 3O2 means you have O2, but then you have 3 of them, right? Okay. So let's remember our law of conservation of mass. In what kind of a system, when we're talking about a system here, in a closed system, subjected to no external forces, the mass is constant, irrespective of its changes in form. Okay, so this would mean if you had a plastic bottle and the lid was on it, and you had, let's say, 100 milliliters of water. Well, that's a fair amount. Let's say 50 milliliters of water, a little bit of water in a bottle, in a closed water bottle. It's now a closed system. It doesn't matter if you freeze that water in there, it's still going to maintain its mass. It's not going to get any heavier because it's now ice. And if you were to heat it up and turn it into water vapor, it would expand and it might cause that plastic bottle to expand eventually. But again, its mass is not going to change. Maybe the volume it takes up will. So the principle that matter cannot be created nor destroyed is the law of conservation of mass. So you can simply state the law of conservation of mass by saying that matter can neither be created nor destroyed, therefore mass can neither be created nor destroyed. So what are our three main types of chemical reactions? All right, so we have a synthesis reaction. And this is when you take two or more elements and combine them to make a more complex substance. You synthesize something new. Or you can have decomposition. And in a decomposition reaction, you have two compounds that break down into simpler products. And that is because it has decomposed. Your compound has decomposed. And then you have a replacement reaction. And this is when one element replaces another in a compound, or two elements from two different compounds switch places. And you'll see some examples of this, so you'll understand it a little better when you see them. So let's talk again a little bit more about open and closed systems. Matter can escape to or enter from the surroundings if you have an open system. See how that flask is open at the top. And if matter cannot leave or enter the system, you have a closed system. And you can see here that there's a stopper in the top of that flask. All right, from your notes, understanding main ideas. Complete the table, balance each equation, then indicate whether the reaction is synthesis, decomposition, or replacement. Okay, and we're going to practice balancing equations together. But what you would get here is FeS plus 2HCl yields FeCl2 plus H2S. And this would be a double replacement, a replacement reaction, but one that we would call double because they both switch places. So you can see that you started with iron and sulfur together. And then over here, you had hydrogen and chlorine together. But in your products, you have iron and chlorine together and hydrogen and sulfur. That is why it's a double replacement. For your next reaction, you would get 2Na plus F2. I think that should be, and that should be a subscript. It got kind of messed up there, sorry. That should be a subscript, that 2. And that would be a synthesis reaction. And then you can get this one, 2HGO yields 2Hg plus O2. So you're seeing what's happening here, right? You have two mercuries and two oxygen because it's all in the front. And then out here you have 2 mercury and 2 oxygen, but they're separated, and that's a decomposition reaction. So if it uses symbols and formulas to show chemical reactions, it's called a chemical equation. A reaction in which compounds are broken down into simpler substances is a decomposition reaction. The number telling how many molecules of a substance are involved in a chemical reaction is a coefficient. A substance present after a reaction is a product. A substance present before a reaction is a reactant. A reaction in which substances combine to form a more complex compound is a synthesis reaction. A reaction in which one element replaces another in a compound is a replacement reaction. And lastly, the principle that states that matter is not created nor destroyed during a chemical reaction is the law of conservation of mass. So describe in words the reaction represented by the equation, and include a description of the composition of each kind of molecule. All right, so how would we say this? We would say 2 molecules of hydrogen, here they are, each containing 2 atoms of hydrogen. So here's our 2 atoms, and this makes it 2 molecules containing 2 atoms, combined with 1 molecule of oxygen containing 2 atoms of oxygen. There it is right there, right? In a synthesis reaction to form 2 molecules of water, each containing 2 atoms of hydrogen and 1 atom of oxygen. Use the law of conservation of mass to explain why the equation here is balanced. The number of atoms of each element must be equal on each side of the equation. The equation for the formation of water from hydrogen and oxygen must be balanced to obey the law. So how do we balance these equations? Okay, we're going to have a little bit of practice here. And then what we're going to do for lab this week is we're going to have an entire lab that is just practicing balancing equations instead of doing what we would have done had we met in class. So you'll get lots of practice. All right. We're going to work through this one step by step. I'm going to explain it to you, and then you're going to do it again when you go over to the lab video. The first thing you're going to do is draw your bracket. Do this methodically, and seriously, probably get a paper and pencil and copy these steps down as I work through them so that you're doing them along with me. That's probably going to be the easiest way to kind of keep up with what's going on. So you draw your little bracket. It looks kind of like a T with a little stick on the top. And then you place your reactants and products on opposite sides of that bar. Reactant, product. Do you agree? Yes, there they are. All right, and then what you're going to do is you write the total number of atoms of each element on each side of the bar, but you have to use the following order. And it's metals, non-metals, except for hydrogen and oxygen, and then hydrogen and oxygen. You have to do it in that order. So if you come back to class next week and you have written down for me on a piece of paper a good mnemonic to memorize this order right here, I'll add a point to your lab. So these will be metal, non-metal, hydrogen, and oxygen. So you want something that's MnHO, kind of like, we did King Henry died unusually, blah, blah, blah. Same idea. See what you can come up with. So you're going to write them down. We have 2 iron, then we have 1 carbon, then we have 3 oxygen. So there's our metal. And then we did them just in order left to right. And then we had the non-metal, not really a situation. So then we got down to the oxygen. Same thing here, in the same order on both sides. All right. So now what we have to do is we're going to look at these relative amounts, these ratios. So first balance the metals, next balance the nonmetals with hydrogen and oxygen last. Now remember, you can't change subscripts, but you can change coefficients. If you add a coefficient anywhere, be sure to change the number of all the elements it will alter. So here's how this works. How many iron do we have? We have 2. How many iron do we have? We have 1. They're not the same. So we need to turn him into 2. How do we do that? We can't add a subscript. We can add a coefficient. There it is. 2. 2 iron. All right. Good. 2 and 2. Check. Moving on. Carbon. We have 1 carbon. We have 1 carbon. Are we good? All right. We're good. Moving on. Oxygen. We have 3 oxygen. We have 2. Oh, that's not good. Now what do we do? Now this one may be a little trickier. How did we get from here to here? We just added 1, but how do we fix this situation? Easiest thing to do, it's kind of like when you're balancing fractions or working with fractions, multiplying them and whatnot. Look, you can just multiply these times each other. So if we do 2 times 3, we're going to get 6. All right, so we need 6 oxygen. How do we get 6 oxygen? We can't change this, but what can we do? We can add a coefficient. We put 3 here. We now have 6 oxygen because we have 3 pairs. All right. So then we have to go over here and go, well, this isn't 3 anymore. We're going to multiply it times 2 to get 6. So now how are we going to fix that? Well, we have 3. So what do we need to do? We can't change the subscript. We have to change the coefficient. We have to put a 2 here. Now we have 2 groups of 3. That's 6. All right, so we're good. 6 and 6. So we're done, right? No, we're not done because now we messed with stuff. So now we got to go back to the beginning and look at it again. So now we've balanced our first non-metal and we got to go check that all our metals are still balanced. So let's see. What do? We go back to the beginning and we say, man, we don't have 2 anymore, do we? How many do we have? We have 4. Oh, and now how many do we have on this side? We still have 2, but we don't want to keep 2. We want to have 4. How do we fix that? Well, that's an easy one. You just make it 4. Now you have 4. Do you agree? 4, 4. Check. So now we check out our carbons. We had 1 and we have 1. Well, we still have 1 on one side, but we don't have 1 over here anymore, do we? We have how many? We have 3. How do we make it 3 over here? We add the coefficient, and now we have 3. 3 and 3. Are we good? We're good. Check back on our iron. 6 and 6, are we good? We're good. And you did it. That equation is balanced. Congrats. All right, now check your notes and then we'll practice some more. Let's see. Here are our notes. State the law of conservation of mass. In ordinary chemical changes, mass is neither created nor destroyed. Using the law of conservation of mass, explain why the following reaction is wrong. Hydrochloric acid plus sodium hydroxide yields sodium chloride. Well, the mass is not conserved because your hydrogen and oxygen just disappear, so that can't be right. Both sides, how can you tell when an equation is balanced? Both sides contain an equal number of atoms of each element. Consider the following balanced equation for the reaction between iron, metal, and water. Is the 3 in 3Fe a subscript or a coefficient? It's a coefficient because we talked about how when you're doing all this balancing, you don't change the subscripts, right? And clearly it's in front, so it's a coefficient. What is a subscript in the water molecule? And it's a 2. There it is. Coefficients change how does changing a coefficient differ from changing a subscript? Coefficients change the amount and subscripts change the structural identity of the substance. Why is iron balanced as 3Fe instead of F3? Subscripts can't be changed as they affect the structural identity of the substance. Sorry, I can't talk. So scan this on your phone. This is a website that will let you practice balancing, and it has varying levels of difficulty. It's a lot of fun. Take some time and spend some time practicing it because you'll be doing a fair amount of balancing in class, so it's helpful to know how to do it well. So after you've done that, go on over, do your lab. Your lab is, we're just going to replace lab 11, like I said, with this video. And if you do have colored marshmallows at home you can use, go ahead. And if not, you can use M&Ms or Skittles or anything else that you might want to work with. Or you can skip the tactile part and move straight to the numbers. See you next week.